Okay, y'all, this is a tricky problem because we're being asked to eventually sketch a possible graph of f of x, that's the original function, but we're given a graph of the derivative. What? Okay, so let's ignore all this for a minute. And let's just say, if I was trying to graph the original function, what information would I need? Well, some points on the graph would be nice, but we don't have those. That's why it's a possible graph of the function. But I would need to know something about the first derivative, so I would probably create a first derivative sign chart, and that'll tell me local extrema, local mins and maxes, slopes of tangent lines of the original f of x graph. And I would need the second derivative sign chart. That'll tell me the shape or the concavity of that f of x graph. Okay. Well, I can get information about f prime of x directly off the graph that was given to me because this is a graph of f prime of x. Okay, so let's just think about that a little bit. What important point do I need on my f prime of x sign chart? What are my partition numbers? I need some kind of number where my derivative either comes out to be 0 or it's going to come out to be undefined, right? If I put that number in. Well, I can see here from the graph that they gave me that this is a nice, pretty polynomial function, no holes or jumps or asymptotes or anything. So I don't have to worry about this case where it's undefined. I just have to worry about where the derivative is 0. And here's the really tempting thing to do, is to pick this point right here. Because you're like, ooh, I see a horizontal tangent line, boom, 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 right here, horizontal tangent line. The derivative is 0 at that point. And that is true. The derivative of this graph is 0 at that point. But this graph is already f prime. So the derivative of f prime is 0 at this point. And what's the derivative of the first derivative? That's the second derivative, right? So this is really telling me the second derivative when x equals 0 is 0. What's the first derivative? If I put 0 into this first derivative function, it hits a height of 2 right there. So the first derivative is 2, but its derivative has a horizontal tangent line. So the second derivative would be 0 at that point. Same thing happens over here. Okay, there I see another horizontal tangent line happening. So what in the world does that mean? That means that the derivative of what was graphed is going to be 0 at that point, and that point is x equals 2. So that means the second derivative at x equals 2 is going to be 0. And it happens that the first derivative is also 0 there, right? Because I can see that this point right here is 0, 0. And what's been graphed? F prime of x has been graphed, so that's my output. So this is 0, f prime of 0. So f prime of 0 is 0 there. So it just so happens they're both 0. But I'm going to put that information on my second derivative sign chart. Not my first derivative sign chart, my second derivative sign chart. So let's go ahead and do that. I'm going to come put that information down here. Okay, so I have two partition numbers. I have x equals 0 and x equals 2. At x equals 0, the second derivative was 0. And at x equals 2, the second derivative was 0. Let's go back up here and think about this f of x business. Like what are the partition numbers on this number line? Well, where is the height of this graph 0? Well, the height of the graph is 0 on the x-axis. So I'm going to look at those x-intercepts. So this point right here, what is that? A -1? At -1, there's a height of 0. Now the tangent line at that graph is positive, so if I put -1 into the derivative of that, remember that the tangent lines are the derivative of what's being graphed. If f prime is being graphed, the tangent line is describing f double prime. So this tangent line is pointing up, so the derivative would be some kind of positive number there. The derivative of the first derivative, so the second derivative would be positive, but the output, thinking just order pairs, inputs and outputs of this graph, at -1, the output is 0, the output is f prime of x, so at -1, f prime is 0. So that's going to be a partition number on this number line, -1. If I put -1 into the graph of that function, I get 0 out. So it's a 0 right there. And again, on this point over here, again, when x equals 2, if I put 2 into that graphed function, a height of 0 comes out. So that's also going to be a 0. Okay. So now let's think about those pluses and minuses on the sign chart here. I'm actually going to start down here with the second derivative sign chart, because that's just the tangent lines of the first derivative graph, right? So I'm just going to read the tangent lines of the f prime graph to get information about its derivative, which is f double prime. So my tangent lines start off pointing up. So that's going to start off positive, and then eventually they level out and hit 0 there. Okay. Then my tangent lines point back negative for a while. Then they hit 0, and then they're going to point back up. So my tangent lines turn positive. So then I'm going to have plus signs after that inflection point. Okay, so now we have that second derivative sign chart all filled out. So let me erase these tangent lines here. Okay, now for the f prime sign chart, I'm just going to read the inputs and outputs of the f prime graph. Just going to read those inputs and outputs. Are they positive or negative? Are those outputs positive or negative? Let's see. So we've already established where the outputs are 0. At -1, the output was 0, and at +2, the output was 0. Okay, so let's just pick a test point. I don't know. Let's test x equals 0. That's between -1 and 2. Well, when x is 0, I'm at this point up here. So if I input a 0 into this f prime graph, what does that come out to be? It's not exactly, it's like 1, 2, not quite 2.5. I don't know, like 2.4 or something. I don't know. We don't care the exact number. We just care that that's positive, right? Because the test point is just telling us the signs on our sign chart. So I got a positive number out. So I'm going to put pluses there. Okay. And then let's test, I don't know, let's test x equals 3. When x equals 3, so 1, 2, 3, I'm at this point on my graph. So if I put 3 into the graph, which is f prime, the output is a height of 2 there, which again, that's positive. So I'm going to put pluses on this part of my sign chart. And then a test point over here, I don't know, let's do -2. So -2 would be right here. And I come, whoa, I'd be way down here somewhere. I don't know how far down I'd go, but I'm definitely having a negative output. So those would be negative values right there. Okay, well, we have both of our sign charts. Now we can use those to get a sketch of the f of x graph. Okay, so before we sketch the f of x graph, here is my advice to you. Do not look at that graph after you create these sign charts. Only use the sign charts to create the possible f of x sketch. Do not look at the original graph. It might mess you up, okay? So I'm ignoring that. Okay, and I'm ignoring all this information. I'm just going to look at the sign charts. Let's just look at the sign charts. Here we go. I'm sketching a possible graph of f of x. So I'm going to label my y-axis f of x. Okay, what are the important points? Let's start with local extrema. Remember that f prime sign chart tells me the local extrema, the local mins and maxes, extrema of the original function. It also tells me about slopes of tangent lines on the original graph, because it's the derivative of the original function, right? On f of x. Okay, so let's do that. So my tangent lines are going to point down, and then they're going to go to 0. So my graph goes horizontal, then they point back up. So I'm going to have a local min at -1. That is going to be a local min. Now here's the deal. I don't know how low to put that local min. That's why it's a possible graph. I don't know where it's located. I could put it up here. I could put it on the x-axis. I could put it down here. It doesn't matter. There's a lot of right answers, okay? So I'm just going to really exaggerate it and put it down here maybe. So my tangent line is going to go horizontal there, but I'm going to hit this local min. I don't know how far down it is, but there's a local min at x equals -1. And then the other important point here is when x equals 2, 1, 2, 3, again, I don't know where to locate that, but it has to be above the minimum, right? So I don't know. Let's just put it right here. I could put it here. You know, basically I could put that point anywhere. Now that I have that min established, you know, this is my min. I could put that point anywhere on that vertical line as long as the input stays right above or right in line with that x equals 2. So I just chose to put it here. And is that point a local extrema? Let's look at our graph. Well, I went from positive sloping tangent lines to positive sloping tangent lines. I mean, I hit 0, so I'm definitely going to have a horizontal tangent line. My graph is definitely going to go horizontal there for a split second. But that is not a local min or max because my sign chart did not change from positives to negatives or negatives to positives. So I'm going to go flat, but I'm going to go from like positive sloping tangent lines, go flat for a minute, and keep positive sloping tangent lines. But I'll connect those in a minute. So I'm going to go horizontal when x equals -1, and that's going to be a local min. I'm going to go horizontal when x equals 2, and this is not a local extrema. Okay, so I'm using that first derivative sign chart to identify those local extrema and to think about the tangent lines. In this case, they're both horizontal. Now I'm going to connect those dots with concavity. So I'm going to go concave up to concave down when x equals 0. Now, x equals 0, where should that go? All I know is it needs to go between these 2 points that I've already graphed. So somewhere, you know, it has to line up with the input x equals 0. So somewhere on this vertical line there, I might as well put it at the origin, right? I don't know. Why not? Let's just put it there at the origin. Okay. So at that's going to be an inflection point because I'm going from concave up to concave down. And I'm going to have another inflection point when x equals 2. So let me just label those inflection points. So this is going to be an inflection point at x equals 0 and another one at x equals 2. These are inflection points. Okay. But I'm going to connect that concave up. So until I hit x equals 0, all in this region, I need concave up going on. So I'm going to connect those with concave up. And it's just a possible graph, so I don't know, maybe like that. Okay, and then in this next region here, between 0 and 2, so between 0 and 2 on my x-axis, so in this region somewhere in here, I need to go concave down. So I need to connect those points going concave down, and it flattens when I hit x equals 2. Okay, and then after that, I'm going to go back concave up. Over here, this is going to be concave up again. So picking back up when x is 2, all in this region, I need to be concave up. And of course, it's flat there when x equals 2, so I'm really emphasizing that horizontal line, and then I'm going concave up. Okay. Okay, so there's our possible sketch of the original function. And just to be safe here, I'm going to label some things. You know, this region right here, that was my concave up region. So I'm just going to label that concave up, just to make it really clear that that was intended to be concave up. And then I shifted to concave down in this region. So I'm going to label that concave down. And then again, it shifted back to concave up after that. So this part of my graph, I'm intending it to be concave up. It looks concave up, but I'm still going to label that as concave up there, just to be safe. And I've labeled my local min just to be safe. Kind of emphasize those horizontal tangent lines just to be safe. And again, this is just a possible sketch. And I'm going to come check it a little bit. So now I'm going to peek back up here. I'm going to unscribble over all this here. Okay. So just another way to check yourself here. Your original graph, or sorry, the graph you were given was of the derivative, right? And if you use your algebra knowledge, this graph was cubic. It was cubic and it was had a positive leading coefficient. So if you remember that from algebra, if you know that your derivative was a cubic function and you think, okay, if I worked backwards, if I reverse that power rule, what degree would I expect to have? Well, the power rule decreases the degree by 1. So if I worked backward, I would increase it to 4. So I'd expect my original function, which I sketched a graph of down here, to be a degree 4 function. That means it's even. That means the ends point the same direction. And since it was a positive leading coefficient on the original, on the graph I was given, it would be a positive coefficient here, which means both ends are going the same direction because it's even, and they're both going up because my leading coefficient would be positive. So I'm pretty sure this graph is right because it's kind of matching what my algebra tells me it should be. But anywho, just my word of warning is read very carefully on these problems. Always stop and ask yourself, what was graphed? Look above that y-axis. Did they give me the original function? Or did they give me, well, in this case, the first derivative? Because what I've seen a lot here on this type of problem when students make mistakes is that they read this graph like it was the original function, and they get these beautiful sign charts, and then when they sketch their graph, you know what they do? They sketch this exact same graph back. The exact same graph. Because they were treating it like it was the original function. If you're treating this like the original function to get your sign charts, and then you use the sign charts to graph, of course you're going to get this picture back, right? You just graphed itself, but it's not the original function. So just read carefully, slow your brain down, and label, label, label.